To start, I would like to ask you a question. When you hear the word drift, what comes into your mind first? Yes, it can be an act of driving something along, a flow of a wind or an ocean, and etc. But in earth science, it is something beyond that. Drifts are usually linked to continents. We call it continental drift. Continental drift has underlying theories and evidences that we will know later. Continental drift is actually a theory that explained that continents had once been joined together and have slowly drifted apart by some unknown mechanism. It was believed approximately 255 million years ago that Earth was composed of one supercontinent that we call Pangaea. It is a term that is etymologically composed of the following words: Pan, which means all, and Gaea means land. Further, this supercontinent was also described that is surrounded by a superocean called Panthalassa. It is also known as Panthalassic Ocean or Phantalassan Ocean. The continental drift was first proposed by Alfred Wegener, a German meteorologist and not a geologist. Scientists did not accept Wegener's theory of continental drift. The problem is that Wegener thought that the continental plates, which are actually really, really large, and the ocean plates, that the continental plates were somehow pushing their way to the oceanic plates. Oceanic plates are really, really dense, and so other scientists at that time said that they wouldn't have the momentum to be able to push through the rocks. And so the theory kind of fell apart. And so Alfred Wegener actually didn't spend most of his career studying plate tectonics. He ended up being a meteorologist for most of his career, and he ended up dying in Greenland. One of the elements lacking in the theory was the mechanism for how it works. Why did the continents drift and what patterns did they follow? Wegener suggested that perhaps the rotation of the Earth caused the continents to shift towards and apart from each other, but it is actually not the case. It doesn't show. As they go along for years and investigate about the theory, there were evidences found in some references. They have identified 5 evidences that include the Fifth continental shoreline, distribution of glacial sediments, paleoclimate, distribution of fossils, and distribution of rocks. Let's tackle first the continental shorelines. It was first suggested by Francis Bacon in 1620 when first world maps were produced. In the evidence, it was observed that there was apparent fit of the continents along their coastlines as pieces of a jigsaw puzzle. Next, we have the distribution of glacial sediments. Glacial sediments or glacial deposits, for example, the tillites, as you can see on the upper left corner, are from rock strata that were once covered with snow. These deposits were found in South America, Africa, Madagascar, Arabia, India, Antarctica, and Australia. Note that these places are known to be tropical and desert-like, such as Africa, Madagascar, and India. Finding ice deposits would seem unreasonable, yet current tropical regions were once near the South Pole. Moving on, we have paleoclimate. Paleoclimate includes coal. Coal is a fossil fuel that originated from the chemically altered remains of prehistoric vegetation. Usually, coal is found in tropical areas because the climate is warm and ideal for propagation of organisms. But before bituminous coal deposits found in cold areas, current cold areas were once in equatorial regions. Next on the list is the distribution of fossils. It was discovered that there were remains of freshwater reptiles such as Mesaurus, freshwater reptile found in Brazil and in Africa. In those era, freshwater reptiles are not capable of swimming to distances between continents. Additionally, plant remains were also retrieved. Geologists found fossils of Glossopteris, a fern plant, which was found to have thrived in 5 different continents, such as Africa, India, Australia, South America, and Antarctica. However, we have to take note that with the absence of flying vehicles, it would be very impossible to any avian organism to have carried with its seed for pollination. Lastly, we have the distribution of rocks. The rock types found in Brazil, India, South Africa, and Antarctica seem to have similar layers and sequence. The theory is that all these places were once continuous and shared the same environment. The next theory that we will be discussing is the seafloor spreading theory. What is a seafloor spreading theory? Are there any evidences that it actually happened? Who discovered this theory? What drives its movement? The seafloor spreading theory supports the continental drift. It is a process that occurs at mid-ocean ridges, where new oceanic crust is formed through volcanic activity and then gradually moves away from the ridge. Later on, we will know each process that took place in this theory. In this theory, the sediments are actually becoming thicker and older. With increasing distance away from the center of the ridges, this means that we can observe that sediments overlying the older seafloor should be thicker and older compared with those overlying newly formed seafloor. Later on, we will thoroughly discuss each process that took place in this theory. The theory was suggested by Harry Hess. He is a geologist who wound up serving as a naval commander during World War II. It was during this time that he made many of the observations and measurements that would provide the foundation of plate tectonic theory. His ship was equipped with sonar and he was able to study the seafloor. America was keenly interested in the seafloor because of submarine warfare. If seafloor spreading drives the plates, what drives seafloor spreading? Here is a summary of important events that actually happen with the process. First, hot mantle from the 2 adjacent cells rises as the ridge axis, creating new ocean crust. Second, the top limb of the convection moves horizontally away from the ridge crest, as does the new seafloor. Third, the outer limbs of the convection cells plunge down into the deeper mantle, dragging oceanic crust as well. This takes place at the deep sea trenches. Fourth, the material sinks to the core and moves horizontally. Lastly, the material heats up and reaches the zone where it rises again. There is a phenomenon called mantle convection. Mantle convection drives plate tectonics. Hot material rises at mid-ocean ridges and sinks at deep sea trenches. This keeps the plates moving along the Earth's surface. Here is an animated demonstration of how mantle convection happens. As we can recall, convection is the process by which a less dense material rises and more dense material sinks. Every day, examples of convection in liquids include lava lumps or water heating on a stove, but the mantle is in general solid. It turns out that rocks, along with most of other solids, flow by a solid state creeping motion, especially when they are hot and given enough time. This is what happens in the mantle. Based on observations of the rates at which the surface of the Earth moves, geologists estimate the mantle convectively flows at rates at several centimeters a year. The heat-driving mantle convection has 3 sources. First, the primordial heat, which is the leftover from the accretion and differentiation that led to the formation of Earth's core, contributes 20 to 50% of the heat. Heating due to the decay of radioactive isotopes, the second one, and the third one is the tidal friction from the moon's pull on the Earth that contributes perhaps 10%. Mantle convection is the main mechanism by which this heat escapes from the interior of the Earth. In the animation, gravity causes older, denser lithosphere to slide away from the ridge down to the sloping asthenosphere. As the older, denser lithosphere slides away, new molten magma wells up at the mid-ocean ridge, specially becoming new lithosphere. This opposing movement of forces is called the ridge rush. Moreover, another important force that we can notice in the illustration is at a subduction boundary. One plate is denser and heavier than the other plate. The denser, heavier plate begins to subduct beneath the plate that is less dense. The edge of the subducting plate is much older and heavier than the mantle, so it continues to sink, pulling the rest of the plate along with it. Scientists call as convection cell or convective flow. But where's the heat source keeping our Earth so performing its circular gymnastics? Well, most of it is left over from the spectacularly energetic collisions and gravitational crushing that created the Earth to begin with. It's still trapped down there, and it wants out there's something else in the molten depths that makes it pretty hot real estate radioactive material. The belly of the beast has plenty of uranium and other radioactive elements, all of which release heat as they decay. That decay has significantly slowed the rate at which the Earth is cooling. So that what does this mean? That at the surface, two things: first magma, then work up along the ridges, those places like Iceland where the Earth is tearing itself as under is pushing the plates in their respective continents apart. Second, what goes on the other end of those plates, the collision zone, may be equally important here, where the heavier plates dive under the lighter ones, yanked downwards by gravity. They halt along the plates back to the oblivion of the mantle. That's what we know or what we think we know, but the details of what's going on in the deepest part of the Earth that drive the engine of plate tectonics, we may never know that too. Let's go now to the concept of plate tectonics. We are already done discussing theories that might have been great support to this. What is really plate tectonic? How did it exist? Why is this relevant? The portion of Earth makes up the plates in plate tectonics. What does the portion of it? Again, the answer came about in part due to war. In this case, the Cold War during the 1950s and 1960s, scientists set up the seismograph networks to see if enemy nations were testing atomic bombs. These seismographs also recorded all of the earthquakes around the planet. The seismic records were used to locate an earthquake's epicenter, the point on Earth's surface directly above the place where the earthquake occurs. Why is this relevant? It turns out that earthquake epicenters outline the plates. This is because earthquakes occur everywhere plates come into contact with each other. The lithosphere is divided into a dozen major and several minor plates, as shown in the figure. A single plate can be made of all oceanic lithosphere or all continental lithosphere, but nearly all plates are made of a combination of both. The movement of the plates over Earth's surface is termed plate tectonics. Plate moves at a rate of a few centimeters a year, above the same rate of a fingernail's growth. A plate tectonics is a large chunk of lithosphere that can carry continental crust, oceanic crust, or some of each. The movement of the plates over Earth's surface is termed as plate tectonics. Ultimately, the discovery of plate tectonics unifies the concepts of continental drift theory, seafloor spreading, and magnetic field reversals. It states that the lithosphere is not a continuous layer, but consists of several irregularly shaped pieces called tectonic plates. In the illustration, you will see an enumeration of the 7 major tectonic plates, with its minor continents and oceans. In the list, the Pacific Plate is the largest, while the South American Plate is the smallest. Plate tectonics have plate boundaries. These plate boundaries move in different directions. They are classified into 3 types, which include convergent, divergent, transform boundaries. You may notice terminologies written below each boundary. These terms are the key terms or words in differentiating them from one another. Plates move away from, toward, or slide past each other. So we have the convergent, the divergent, and the transform. To start, convergent plate boundaries happens when 2 plates collide. It occurs in the subduction zones when one or both of the tectonic plates are composed of oceanic crust. The denser plate is subducted remain or underneath the less dense plate. The plate being forced under is eventually melted and destroyed. Convergent plate boundary is further classified into 3. These are the oceanic-oceanic collision, oceanic-continental collision, and the continental-continental collision. Oceanic-continental collision happens when oceanic crust meets ocean crust. Oceanic-oceanic convergence occurs when the leading edge of both plates consists of oceanic crust. These plate boundaries have many of the same features as in oceanic-continental convergence. In oceanic-oceanic convergence, a volcanic arc is a chain of volcanoes. An island arc is formed from the subduction of an oceanic plate beneath another oceanic plate. Continental volcanic arc is formed from the subduction of oceanic plate beneath a continental plate. Also, island arcs and oceanic trenches occur when both of the plates are made of oceanic crusts. Zones of active seafloor spreading can also occur behind the island arc, known as the back arc basins. These are often associated with submarine volcanoes. One example of trench is the Mariana Trench. They form when 2 tectonic plates collide. At the collision point, one of the plates drives beneath the other into the Earth's mantle, creating an ocean trench. The depths of the Mariana Trench were first plumbed in 1875 by the British ship HMS Challenger as part of the first global oceanographic cruise. Next is the oceanic-continental collision, where oceanic crust meets continental crust. Oceanic-continental convergence occurs when leading edge of one plate is composed of continental crust that is granitic and the other is oceanic that is basaltic. The denser oceanic plate dives beneath the subducts the lower density continental plate. Lower density, which is granitic rocks, tend to float in the asthenosphere, which is the upper portion of the mantle. Lastly, we have the continental collision, where continental crust meets continental crust. Continental convergence defines a plate margin where the leading edge of both plates contains continental crust. When two continents collide, neither a continent is subducted because the continental rocks have a relatively low density. As a result of the convergence, the crust tends to deform and be pushed upward like a mountain building. This type of plate boundary is associated with mountain building. The Himalayan mountains are excellent example of this type of convergence, where the Himalayan mountains and the Tibetan plateau are a result of crustal deformation and thickening from the convergence of the Indian and Eurasian plates. The second type of plate boundary is the divergent boundaries. It is known to be a movement of two plates apart or away from the other. The magma comes out from the center of the ridge and eventually it solidifies into basalt, producing a new oceanic plates. The lithosphere cracks producing normal faults. The slips along these faults are primarily cause of earthquakes in divergent boundaries. The space created can also fill with new crustal material sourced from molten magma that forms below. Divergent boundaries can form within the continents but will eventually open up and become oceanic basins. Further, it may take place on land and under the sea. On the land, let's proceed on the land. The divergent boundaries within continents eventually produce rifts, which produce rift valleys. A rift valley is a linear-shaped lowland between several highlands or mountain ranges created by the action of the geologic rift or fault. A rift valley is formed on a divergent plate boundary. It is a crustal extension of spreading apart of the surface, which is subsequently further deepened by the forces of erosion. While under the sea, the most active divergent plate boundaries are found between oceanic plates and are often called mid-oceanic ridge, such as the mid-Atlantic ridge, which splits nearly the entire Atlantic Ocean north to south. Last type of plate boundaries are the transform boundaries. These plates slide past each other. The relative motion of the plates is horizontal. They can occur underwater or on land, and crust is neither destroyed nor created. Because of friction, the plates cannot simply glide past each other. Rather, stress builds up in both plates, and when it exceeds the threshold of the rocks, the energy is released, causing earthquakes. Although most transform boundaries occur in the ocean basins, a few occur on land. The San Andreas Fault system is a transform fault that connects two ocean ridge systems, the East Pacific Rise in the south to the Explorer Ridge in the north in California. The San Andreas Fault is the transform boundary between the North American plate and the Pacific plate. We also have the Wilson cycle. It is a model proposed by J. Tuzo Wilson. He is a geophysicist. It explained the process of the opening and the closing of an ocean caused by movement of the Earth's plates. The Wilson cycle begins with a hypothetical geologically or tectonically quiet continent. Rather, the model is divided into 9 stages, but the stages are arbitrary and they do not exist naturally. Within the Earth is an ongoing series of processes. It is more important to understand these processes, how they are related, and how one process leads to the next process. Also note that the Wilson cycle is a simple, ideal model. In reality, the Earth has many continents which migrate across its spherical surface in very complex ways. Now we could see on the video the Wilson cycle, the animation of which. Again, it is the opening or the beginning and the closing or the end of an ocean. We also have here an example of Wilson cycle with 7 stages. Remember that the stages are arbitrary. The series of events might not be the same to the other continent of Earth. The only thing that you need to remember is that it starts with the uplift and crustal extension of continental areas with the formation of rift valleys, and it ends when once all of the oceanic crust between the continental masses has subducted and the continents converge along a collision zone characterized by an active fold mountain belt such as Himalayas. Finally, the plate boundary becomes inactive, but the site of the joint or suture between the two continental masses is a zone of weakness. In the lithosphere, that has a potential to become the site of a new rift, and so the cycle continues. We can measure how fast tectonic plates are moving today, but how do scientists know what the rates of plate tectonics or movement have been over geologic time? The oceans hold one of the key pieces of the puzzle. Because of the ocean floor magnetic stripping records of the flip-flops in the ocean's magnetic field, scientists, knowing the approximate duration of the reversal, can calculate the average rate of plate tectonics during a given time span. These average rates of plate separations can range widely. Did you know that the Arctic ridge has the slowest rate with less than 25 centimeters a year, and the East Pacific rise near Easter Island in the South Pacific, about 3,400 kilometers west of Chile, has the fastest rate, more than 15 centimeters per year? Don't worry, we won't be computing them in this course. Plates move at about the same rate as human fingernails grow, like a few centimeters a year. Let us remember that plate tectonics are conventionally observed with the following feature. The Earth's surface is covered by a series of crustal plates. The ocean floors are continually moving, spreading from the center, sinking at the edges, and being regenerated. Convection currents beneath the plates move in a crustal plates in different directions, and the source of its driving the convection currents is radioactivity deep in the Earth's mantle.